Hello everyone. In this video, our objective is to measure frequency using an AC bridge. So in our last couple of videos, we have already seen that how to measure different kind of passive components values like resistance, capacitance, inductance using AC or DC bridges. So today we are now going to measure frequency using a Wien Robinson's bridge. So let us understand how this Wien Robinson's bridge actually works. Hope my screen is visible to you all now. This is the platform, VLabs platform, where we are going to perform this experiment on Wins Robinson frequency bridge. The link will be given in the description box. Okay. So this is the AC bridge configurations which can be used to measure frequency of unknown voltage source. Okay. AC voltage source. Now we can easily derive the bridge balance equation from this bridge. Okay. So I am not going to discussing this bridge balance equation. So ultimately, this will be the final expression. And from this equation number one, if you compare the imaginary part and real part, you will see that in the left hand side of the equation, there is no imaginary term. That means the plus j into 0 is there. So there is no imaginary term is missing. So we can infer from this equation number one that this portion, that means omega C1 R2 minus 1 by C2 R2 should be equal to exactly 0, and which is this given by equation number 3. And similarly, R2 by R1 plus C1 by C2 should be equal to R4 by R3 as mentioned in equation number 2. So hope it is clear how this equation number 2 and 3 has been derived. Now from this equation number 3, we can easily say that omega C1 R2 should be equal to 1 by omega C2 R1. And from there, we can get that omega square C1 C2 into R1 R2 is equal to 1, or omega is equal to 1 by square root of R1 R2 and C1 C2. Now see, if we take R1 and R2, I mean R1 is equal to R2 and C1 is equal to C2, then we can calculate that omega is equal to 1 by root of square root of RC. So we can write also small f, which is linear frequency, is equal to 1 by 2 pi of square root of RC. Okay, so that is the nice formula. And now if I put R1 is equal to R2 and C1 is equal to C2, then from this equation number 2, we will get R4 by R3 is equal to 2. And that's why we are taking R4 is equal to twice of R3. Okay, so this is the basic derivation, okay, of this Wins Robinson's frequency bridge. Now, without further ado, go to the simulator link and click here to perform the experiment. Now, this is our experimental setup. Okay, this is for Wins Robinson's bridge. Now, you have to follow the uh, procedure. I am saying that let R3 is equal to, let it be 1000. And we have now seen that R4 should be equal to twice of R3. So that means it should be 2000. So you have to, it is not mentioned over here, but yes, you can keep R3 is equal to 1000 or any value. Okay. And R4 is equal to twice of R3. That means 2000. Correct? My suggestion is start from the basic. So keep it C1 is equal to 0.1, which is the lowest value of capacitance, variable capacitance, and C2 equal to same. Why? For why we are taking C1 and C2 equal to same? Because we have taken R1 should be equal to R2 and C1 equal to C2. So that's why we will get F is equal to 1 by 2 pi of root over LC. Correct? Now, what we can do after setting all these things, fix the frequency, set the frequency as 500 and switch it on. And if you switch it on, then we will see a deflection, a sharp deflection in the galvanometer. Now we have to make this bridge balance condition. That means in galvanometer, it is expected that we have to get the null position, right? Right? So how to do that? we can change the value of actually C1, C2 we have already fixed, and R3, R4 already fixed. So only thing is R1 and R2 we can change. But again, remember to for simple calculation, we have to take R1 is equal to R2. So if I change here, R1 is equal to from 1 to 2. So always we have to take same, number. If we use here 1, then R2 should be also equal to 1. Okay. Now, in this particular platform, there is a, not I will say a problem, but the right procedure is like this. First, switch off the bridge, then only you can change this value from any 1 to 2 or 200. Let's say try with 200, but if you change it here, then you also have to change R2 also. Okay, and then switch it on. You can see there is nothing changed, so the value is still very high. And let me use 2 after that 5 zeros, here also 2 after that 5 zeros, and see there is no change. Okay, we have to do for a couple of times. Yeah, now see here, if I use 2 after that 6 zeros and 2 after that 6 zeros, the value is still greater, but it is less. And now it is comes in 3 digit, it is 510, correct? Now if I increase the value of this resistance further, then see what happens. Yes, it is again, it is increased. So of course we are in a wrong direction. So let me remove this, and instead of 1 2, let me use 1 8 instead. Okay, instead of 20, let me use 1 8, and see it is now from 590 to 620. Okay, so let me use 90, and so that you have to trial and error by, but remember, every time you have to switch off the circuit, and then only you can change these values. Okay, and not only one value, you have to change both the values. Okay, now see, uh, it for 19 lakhs it is 564. So in this way, we have to try to find out the null position. And I have observed in this experiment in VLabs platform, if you are somewhere between +5 to -5, okay, then the then you will be done. I mean, it is enough for this null condition. Okay, not exactly zero. If you do not get exactly zero, then also don't worry. And uh, let's say, let me uh, give you a particular point here. I have already experimented like this. You can see my screen right now. So these are the values. So I have used 1000 for R3, 2000 ohm for R4, C2 and C1 kept 0.1 farad, and then for R1 it is 31840 and 31840. Okay, so we can use this result. Let's say 31840. Let me check once again. 31840. Yeah, so it is coming 1.29. So around this, within this ±5 range. So once it is there, then in this tab, fixed frequency tab, click on calculate. And if it is in this range, I mean +5 to -5, then only your percentage error is less than 1%, and which is very important. For this experiment, your percentage error, calculated percentage error, should not be greater than 1%. Okay, remember that. Otherwise, you will get a erroneous value. Now, if you calculate this, then see your calculated frequency is 500.74. However, our actual frequency of this AC source is 500 hertz. So now that means this is your percentage error already calculated. So you have to now know that how to tabulate it. Okay, in tabulation, you have to mention the value of R3, R4, C1, C2, R1, R2, and what is your actual frequency and voltage. That means actual frequency FD, voltage value amplitude of this source is 5. And then what is your calculated frequency, which can be written like 500.74. Okay. So that is how we have to calculate a observation table, and you have to take at least 3 to 4 different or distinct results. Okay. So that's all for today. Perform this experiment and submit your lab report. Thank you.